January 1941. A frozen testing ground on the American East Coast. The air is sharp. Breath turns white. Boots crunch against packed snow. Downrange, a row of wooden frames stands in silence. Mounted on them are crude vests, thick, layered, awkward. They're not issued. They're not trusted. They are barely understood. A rifle cracks. Then another. .30-06 round strike at full velocity, tearing through air designed for men, not machines. Some rounds punch straight through. Others deform. A few stop, barely, caught inside layers of unfamiliar material. Observers take notes. Army officers watch without speaking. This is not a battlefield, but the stakes feel just as high. By 1941, American soldiers wear steel helmets refined for shrapnel and fragments. But below the neck, there's almost nothing. No modern torso protection. No reliable answer to the rifle bullet. The most common killer of infantrymen in modern war. Across the Atlantic, Europe is already burning. Casualty reports pile up. Gunfire decides survival in seconds. And inside American industry, far from the front lines, chemists and engineers at DuPont are about to collide with a problem the U.S. Army can no longer ignore. Because the next war will not wait for better armor. And what happens next will quietly change how soldiers survive it. The problem confronting the United States in early 1941 did not begin with World War II. It was inherited, and it had been ignored for more than 2 decades. In 1918, the First World War ended with an uncomfortable truth etched into military records. The steel helmet had saved thousands of lives, but had also revealed a limit. Helmets stopped fragments. They deflected debris. They reduced fatal head wounds by measurable margins. They did not stop bullets. During the final year of World War I, the U.S. Army conducted limited experiments with body armor. Heavy steel breastplates, segmented abdominal guards, rigid cuirasses modeled loosely on medieval designs. They worked technically. At close range, some could stop pistol rounds and slow rifle fire. But they were heavy, often exceeding 15 kilograms. They restricted movement, exhausted the wearer, and shifted balance under fire. Infantry units rejected them almost immediately. Officers noted that soldiers carrying steel armor moved slower, fired less accurately, and collapsed sooner under strain. In modern war, speed mattered more than protection that arrived too late. By the 1920s, the lesson hardened into doctrine. Body armor was impractical. Mobility was survival. For the next 20 years, American military development focused elsewhere. Aircraft engines, naval gunnery, artillery, tanks. Infantry protection remained essentially frozen in time. By 1939, when war erupted again in Europe, the American soldier still carried the same fundamental defensive equipment: a steel helmet, a wool uniform, leather boots, nothing more. Across the Atlantic, the reality of modern combat evolved brutally fast. The German invasion of Poland demonstrated what concentrated automatic fire could do to exposed troops. In France and the Low Countries, machine guns and rifles inflicted casualties in minutes that once took days. British medical reports from 1940 painted a consistent picture. A majority of fatal wounds were to the torso, not the head, not the limbs, the chest and abdomen, areas completely unprotected. American military observers took notes. They filed reports. They circulated summaries. But institutional inertia is slow. The U.S. Army entered 1941 still officially neutral, still not at war, still structured around a peacetime budget and peacetime assumptions. Its infantry doctrine emphasized marksmanship, maneuver, and unit cohesion, not individual protection. Yet numbers were beginning to tell a different story. Between 1917 and 1918, approximately 70% of American combat casualties were caused by small arms fire, not artillery fragments, not gas, bullets. By 1940, improvements in rifle ammunition, higher velocities, better penetration, more reliable primers, made those numbers worse, not better. A single .30 caliber round, fired from standard infantry rifles, carried enough kinetic energy to pass through multiple layers of wool, webbing, and flesh without significant deceleration. Helmets did nothing to stop that. The question was no longer theoretical. It was industrial. Could protection be created that did not cripple the soldier who wore it? Steel had failed. Rigid plates were obsolete. What remained unexplored was fabric. Not cloth in the civilian sense, but layered textiles engineered for stress, tension, and impact. During the interwar period, American industry had quietly advanced synthetic fibers for tires, belts, and industrial applications. These materials were light, flexible, strong under load. No one had seriously asked whether they could stop a bullet. By late 1940, as Europe burned and Asia edged closer to open war, that question began circulating inside U.S. military research offices. Not loudly, not officially, but persistently. And it would lead the Army beyond its own laboratories, toward civilian science, chemical engineering, and a corporation whose peacetime innovations were about to collide with wartime necessity. The foundation had been laid. The war had not yet reached American shores, but the clock was already moving. By 1940, American industry was already shifting quietly into a wartime posture, not through declarations, through contracts. The United States was not yet a belligerent, but it was no longer neutral in practice. Factories lengthened shifts. Research budgets expanded. Materials once developed for commerce were reassessed for conflict. At the center of this transition stood the U.S. Army, facing a paradox it could not solve alone. Its weapons were modern. Its doctrine was evolving. But its soldier remained exposed. Steel had reached its limit. Ballistics had outrun metallurgy. Army research divisions understood this by late 1940. Test data from Europe made it clear. Increasing rifle velocity meant penetration was no longer linear. Once a threshold was crossed, rigid materials failed catastrophically. They cracked. They spalled. They transferred lethal energy directly into the body. Fabric behaved differently. Layered fibers absorbed energy gradually. They stretched. They dispersed force laterally instead of transferring it straight inward. The concept was not new. Sailing rope and canvas had been studied for decades, but no one had refined it for gunfire. This gap drew the military into unfamiliar territory. Instead of arsenals, they approached laboratories. Instead of foundries, chemical plants. Synthetic fiber research had exploded during the 1930s. Driven by automotive demand, aviation needs, and civilian manufacturing, American companies had learned how to manipulate polymers at the molecular level. They could create fibers thinner than silk, stronger than steel by weight, and consistent in ways natural materials never were. Nylon was one of them. Originally designed for consumer use, stockings, cords, parachute lines, it displayed properties that caught military attention. High tensile strength, elastic recovery, resistance to tearing. What had never been tested against was a rifle round. By early 1941, experimental requests began circulating, not for finished armor, for data. How many layers would it take to slow a bullet? What angle mattered? What weave density changed outcomes? The Army did not issue public requirements. Instead, it issued questions. Civilian engineers began running impact tests originally designed for industrial stress analysis. High-speed photography, still primitive, captured fibers stretching milliseconds before failure. Energy charts compared penetration depth across different materials. Results were uneven. Single layers failed instantly. So did thin stacks. But beyond a certain density, something changed. Rounds did not pass cleanly through. They deformed. They tumbled. They lost velocity faster than expected. The breakthrough was not stopping the bullet completely. It was reducing lethality. A bullet that did not penetrate the chest cavity did not cause catastrophic organ damage. A bullet slowed enough could be survivable. Medical officers recognized the implication immediately. Even non-penetrating impacts reduced mortality. Blunt trauma was brutal, but it was not automatically fatal. Internal injuries could be treated. Penetrating wounds often could not. At the same time, the Army faced constraints no laboratory could ignore. Any armor had to weigh less than 3 kilograms. It had to be flexible enough for crawling, running, and firing prone. It had to function in heat, rain, and cold. And it had to be producible at scale. In early 1941, America did not have years. It had months. The final barrier was psychological. Infantry commanders distrusted anything that promised protection. They feared soldiers would take risks. They feared overconfidence. They feared history repeating itself. Heavy armor slowing men down and getting them killed anyway. So the research continued quietly. Prototypes remained unofficial. Tests remained classified. Then December arrived. The attack on Pearl Harbor ended all ambiguity. America was at war. Casualty projections soared overnight. And what had once been a theoretical inquiry became an urgent demand. Protection was no longer a luxury. It was a necessity. The question now was not whether body armor could exist, but whether it could prove itself before battlefield casualties proved the cost of delay. That question would be answered not in theory, but through multiple lenses: human, tactical, industrial, and moral, all converging toward the same battlefield reality. For the infantryman, the mathematics of war were simple. Exposure equaled risk, and risk was constant. American soldiers entering training camps in 1941 learned how to shoot, move, and communicate. They learned to trust their helmets. They did not learn to trust their torsos, because there was nothing to trust. Medical data from Europe showed that rifle fire killed not through spectacle, but through predictability. Chest wounds collapsed lungs. Abdominal wounds caused catastrophic bleeding. Survival depended on seconds, not skill. For the man advancing across open ground, armor was not abstract science. It was the space between life and a letter home. Soldiers understood this instinctively. They improvised protection when they could: sandbags in vehicles, scrap metal in aircraft cockpits, steel plates welded into gun shields. But infantrymen had nothing comparable. Morale reflected it. Surveys and informal reports indicated that fear of small arms fire outweighed fear of artillery for many troops. Artillery was random. Rifles were personal. Any promise of protection, even partial, changed psychology. Not recklessness, but endurance. A soldier who believed he could survive a hit stayed functional longer under stress. This human dimension drove urgency far more than doctrine ever could. By 1941, infantry rifles had reached a lethal maturity. Weapons like the M1 Garand fired high-velocity rounds capable of penetrating steel helmets at combat ranges. These rounds carried energy measured not in force alone, but in destructive certainty. Traditional armor failed because it resisted impact rigidly. When it failed suddenly. Layered fibers behaved differently. They stretched under impact, converting kinetic energy into tensile stress. Instead of cracking, they elongated. Instead of transferring energy inward, they spread it sideways. This principle mattered more than thickness. 10 thin layers performed better than one thick plate. Engineers began treating bullets not as penetrators, but as energy problems. Slow the round, deform it, reduce penetration depth. Stopping a bullet completely was rare, but reducing velocity by 40 to 60% often meant survival. Technology was no longer chasing invincibility. It was chasing survivability. Commanders worried about trade-offs. Every added kilogram reduced endurance. Every restriction slowed reaction time. World War II infantry doctrine depended on movement, advancing by bounds, crawling under fire, sprinting between cover. Armor that interfered with that rhythm could be fatal. Testing focused obsessively on weight. Anything above roughly 2.5 to 3 kilograms was rejected. Flexibility mattered as much as resistance. Field trials measured crawl times, sprint distances, firing accuracy. If armor reduced performance by more than marginal percentages, it was reconsidered. The realization was subtle but decisive. Armor did not need to make soldiers invulnerable. It needed to preserve mobility while reducing fatal wounds. Once that balance appeared achievable, resistance began to erode. The debate shifted from should we protect the soldier to how much protection can we afford without losing him to exhaustion instead. That question would now be examined from even broader perspectives: industrial power, ethical priorities, and the enemy's own hard-earned lessons. The U.S. military could define the problem. It could not solve it alone. The solution emerged from industrial chemistry, not traditional weapons design. Inside American laboratories, polymer science had matured quietly through the 1930s. What had once been experimental was now repeatable, scalable, reliable. Synthetic fibers could be manufactured in controlled thickness, consistent weave, and predictable strength. This mattered more than innovation itself. War did not reward ideas, it rewarded production. Civilian engineers accustomed to designing materials for tires, cables, and parachutes now faced a new constraint: ballistic impact. They learned quickly that uniformity mattered more than raw strength. A single weak fiber caused cascading failure. Consistency saved lives. Unlike steel, fabric armor could be sewn, layered, repaired, and modified without specialized foundries. Factories already producing textiles could be converted rapidly. This allowed the United States to move faster than nations dependent on heavy metallurgy. The industrial advantage was not just technical, it was logistical. Protection could now be produced in the same system that supplied uniforms, tents, and web gear, turning armor from exotic concept into a manageable supply item. Once armor became viable, a harder question followed. Not everyone could have it. Early ballistic vests were expensive in materials and labor. Production capacity was limited. Distribution had to be selective. Priority went to aircrew first. Bomber crews faced concentrated fire. Flak and machine guns shredded fuselages. Survivability calculations favored them. Infantry came later. This hierarchy reflected uncomfortable realities. A trained pilot represented years of investment. An infantryman, brutal as it sounds, could be replaced faster. Medical officers challenged this logic quietly. So did some commanders. Statistics showed that even modest torso protection could significantly reduce fatality rates among ground troops. The debate never became public. It unfolded in memos and requisition forms. In war, morality often hides behind logistics. But the question lingered: was protection a privilege or a responsibility owed to those closest to enemy fire? America was not alone in confronting this problem. German forces, particularly the Wehrmacht, had experimented with body protection for assault engineers and sentries. Their steel breastplates were heavy and limited, but they reflected awareness of vulnerability. In the Pacific, the Imperial Japanese Army relied more on discipline and concealment than protection. Body armor was rare. Casualties were accepted as inevitable. Neither approach solved the problem. One sacrificed mobility. The other sacrificed lives. American planners studied both outcomes carefully. They did not seek perfection. They sought balance. By early 1942, the angles converged. Human need, technological possibility, industrial capacity, moral pressure, all pointed toward the same conclusion. Armor could no longer remain theoretical. It had to face gunfire, officially, conclusively, and under conditions that mirrored the battlefield itself. The decisive moment was coming, not in a factory, not in a memo, but in tests where numbers, not opinions, would decide whether protection belonged on the modern battlefield. The tests moved from theory to proof at Aberdeen Proving Ground. Here, variables were stripped of emotion. Distance was measured. Angles were fixed. Ammunition was standardized. What mattered were numbers. Engineers mounted prototype vests on ballistic gelatin torsos calibrated to human density. Layer counts varied, 10, 12, 14, sometimes more. Fibers were woven tightly, then stitched to prevent shifting under impact. Rifles fired at distances replicating combat ranges, 100 yards, 75 yards, 50. At full velocity, most early configurations failed. Penetration was partial but lethal. The bullet entered. The gel ruptured. Then layer density increased. At approximately 14 to 18 layers, depending on weave and orientation, penetration behavior changed. Bullets deformed. Some flattened. Others yawed violently, dumping energy across the surface. Penetration depth dropped dramatically, often below critical thresholds for organ damage. Medical observers focused on trauma patterns. Blunt force injuries were severe. Ribs would fracture. Internal bruising would occur. But lungs remained intact. Major vessels remained unsevered. Survivability increased. The numbers were stark. In repeated tests, torso penetration dropped by more than 60% compared to unprotected targets. Lethality dropped even further. The vests weighed between 2.3 and 2.9 kilograms, within mobility limits. Skepticism persisted. Laboratory success did not equal battlefield survival. So the tests escalated. Multiple impacts were introduced. Angles shifted. Rounds struck seams and overlaps. Failure points appeared and were reinforced. Stitching patterns changed. Layer orientation rotated. Weakness became data. By mid-1942, the results crossed a line the Army could not ignore. These vests would not stop every bullet. They were never meant to. They stopped enough to change casualty curves, enough to justify production, enough to save lives statistically rather than symbolically. Authorization followed quietly, not a proclamation, a requisition order. Production began under wartime urgency. Materials were diverted. Factories retooled. The first units to receive the vests were not infantry divisions storming beaches. They were bomber crews. Air war data demanded it. But the infantry was watching closely. Reports filter back from early users. Hits that should have killed did not. Men walked away bloodied but alive. The proof was no longer confined to targets and charts. It was written into medical logs and survival reports. What remained was the ultimate test: combat, and it would come sooner than anyone expected. Combat does not care about test results. It validates or destroys them without explanation. The first widespread operational use of American ballistic vests occurred in the air war over Europe in 1942 and 1943. Bomber crews faced a storm of steel, machine gun fire, cannon shells, and flak fragments tearing through thin aluminum skins. The vests were issued selectively. Gunners, radio operators, crewmen exposed near fuselage openings. They were not comfortable. They were hot. They restricted movement in cramped aircraft. But the numbers began to shift. Medical reports from the U.S. Army Air Forces documented a measurable reduction in fatal torso wounds among armored crew members. Penetrating injuries declined. Survivable blunt trauma increased. Men who would have died now reached hospitals. The data was unambiguous. Encouraged by this, ground forces pressed their case. Infantry trials expanded in 1943. Assault engineers, machine gun crews, medics operating under fire. In these roles, exposure was prolonged and concentrated. The vests proved their worth. Reports described rounds striking squarely and failing to penetrate. Others noted bullets slowed enough to prevent fatal injury. One after-action summary recorded a reduction of more than 30% in lethal torso wounds among units equipped with armor during limited engagements. Skeptics fell silent. By 1944, the U.S. Army officially recognized ballistic vests as effective protective equipment for specific roles. They were not universal issue. Production could not meet that demand, but their place was secured. The turning point was not dramatic. No single battle marked it. It was cumulative. Every survival report reinforced the same conclusion: armor changed outcomes. It did not win battles. It preserved soldiers long enough to keep fighting them. By the time Allied forces landed in Western Europe in 1944, ballistic vests were a known quantity. Still limited, still debated, but no longer experimental. The infantryman still advanced under fire, still bled, still died, but now sometimes he lived, and that difference, measured in hospital beds instead of graves, reshaped how the military thought about protection forever. What followed was not triumph, but reckoning. Because once armor proved its value, the consequences of who had it and who did not became impossible to ignore. Once ballistic vests proved effective, the war exposed a new reality. Protection was finite. Production expanded, but it never caught up with demand. Between 1942 and 1945, the United States manufactured hundreds of thousands of ballistic vests, not millions. Material constraints, labor limits, and competing priorities ensured scarcity. Distribution followed cold arithmetic. Aircrew remained the top priority. Statistical models showed that a single vest could save multiple trained specialists over repeated missions. Gunners who survived one engagement flew again. The investment paid itself back. Ground forces received armor selectively. Assault engineers breaching fortifications. Machine gun teams pinned in fixed positions. Medics exposed while retrieving wounded under fire. Standard riflemen rarely received vests, not because they did not need them, but because supply could not meet scale. Reports from the European theater in 1944 reveal uneven distribution even within the same unit. One squad might have armor, another would not. This imbalance created tension. Some soldiers felt protected, others felt expendable. Commanders struggled with allocation decisions that had no moral clarity, only statistical logic. Medical data, however, continued to accumulate. Hospital intake records showed that armored personnel arrived with fewer penetrating chest wounds. Survivability increased markedly. Recovery time shortened. One U.S. Army medical summary noted that torso armor reduced fatal injury probability by more than 1/3 in specific combat roles. These numbers mattered. They justified continued production even as the war strained resources. Yet armor never became universal during World War II. The technology worked, but it arrived late. By the time production stabilized, the war's decisive phases were already underway. In Normandy, in the Ardennes, in the Pacific Islands, protection saved lives, but it could not rewrite the cost already paid. As the war moved toward its conclusion, attention shifted again, not to immediate survival, but to what this technology meant beyond 1945. Because the vest was no longer an experiment. It was a precedent. The influence of ballistic vests extended far beyond the immediate war. By 1945, the United States had established a template for protective equipment that could evolve with technology. Nylon and other synthetic fibers, once exotic industrial materials, became central to military research programs. Their potential extended beyond torso protection. Parachute lines, ropes, and even tent fabrics benefited from innovations driven by ballistic testing. The lessons of allocation, production, and prioritization informed post-war planning. Military strategists understood that armor was not a panacea. It was a force multiplier for high-value roles. The ethical debates, who deserved protection first, became institutionalized as formal doctrine. Medics, engineers, and specialized infantry units were automatically considered high priority for protective gear. The direct line from 1941 experiments at Aberdeen Proving Ground to Vietnam-era flak jackets is clear. In the 1960s, U.S. forces deployed flak vests made of layered nylon, capable of reducing battlefield mortality in ways that mirrored the World War II prototypes. The principle remained unchanged. Multiple layers, distributed energy, and careful weight management. Casualty studies confirmed the impact. Soldiers wearing early ballistic vests consistently survived wounds that were fatal to unprotected comrades. Statistical models predicted a 20 to 40% reduction in torso fatalities in specific engagements. Even if numbers could not capture individual lives saved, the trends were unmistakable. The wartime production also established a precedent for industrial military collaboration. DuPont's work demonstrated that peacetime civilian technology could pivot to wartime necessity within months. Chemical companies, textile manufacturers, and engineers became integral parts of battlefield planning. Innovation was no longer confined to arsenals or research labs. It became part of national defense strategy. The cultural impact endured. Ballistic protection became synonymous with the soldier's right to survive under fire. It shaped training, equipment philosophy, and the eventual development of modern body armor that protects infantry, police, and special operations forces around the globe. The war had revealed the stark truth. Survival is not determined solely by courage or skill. It is influenced by materials, science, and foresight. Armor did not win the war, but it preserved the lives necessary to fight it. The stage was now set for reflection, not on battles or production numbers, but on what these innovations meant for humanity, for warfare, and for the role of science in saving lives under fire. In the cold calculus of war, the human body is both weapon and vulnerability. World War II exposed that vulnerability in stark numbers. Men fell by rifles, machine guns, and shrapnel. The story of DuPont's ballistic vests reminds us that survival is often born in laboratories, not on battlefields. Synthetic fibers stretched and layered in quiet rooms, far from gunfire, became the invisible shield for men facing the chaos of modern war. Science, when applied with urgency and precision, turned theory into life-saving reality. Armor did not make soldiers invincible. It did something quieter, yet profound. It gave them a chance to breathe, to crawl, to return from missions that once promised only death. And in doing so, it reshaped how military planners, engineers, and even policymakers thought about the human element in combat. The ripple of these innovations continues today. Modern ballistic vests, lightweight plates, and flexible composite armor trace their lineage directly to the experiments, debates, and tests of 1941 to 1945. What began as a question, can a bullet be stopped, evolved into a principle. Protection is not just equipment. It is a responsibility. In the end, history remembers battles and leaders, but survival remembers those unseen moments of invention. Men live because someone far from the front solved a problem that the battlefield could not forgive. DuPont reinforced not just fiber, but the fragile line between life and death. And in that quiet act of science, the shape of modern warfare and humanity's capacity to protect itself was quietly, irrevocably altered.